Thank you so much for the very kind introduction. I really look forward to visiting at some point. Okay. So today what I will be talking about is, the title of the talk is very broad on, challenges in reliable machine learning. But these are some directions that, me and my group have been working on for the last 3 or 4 years. Okay. So to understand reliable learning, let's look at what happens when we open a textbook of machine learning, right? So if you open one of these standard, somewhat math heavy textbooks in machine learning, this is the situation that you see. So what you see is, typically you look at something like classification. And what happens over here is that you get a bunch of training data, which is generated where each of the training samples is generated independently from some data distribution. This training data feeds into a classifier, into some algorithm, and out comes a classifier, right? So you feed it into a machine learning algorithm, you get some sort of classifier. And then this classifier is evaluated on test data. And this test data is again drawn IID from the same underlying distribution, right? So there's some underlying data distribution. Your training data is drawn IID from it. You use your training data to build a classifier, and then you feed it to test data, which is not the same as the training data, but is drawn from the same distribution, right? And then if you get high test accuracy, what this means is that you have a really good classifier, right? So this is kind of the textbook situation when you open, any machine learning 101 class, it's going to talk about this setting, right? The reality, however, is a lot different. So, for example, there's many issues that arise in reality, which is not, which this particular, very simple situation ignores, and which actually leads to real problems when we try to deploy machine learning in practice. So, one of the issues that comes up is things like robustness, where, maybe at training time, you got your training data from a source. At test time, what happened is maybe you are looking at slightly different kinds of data, right? So maybe you were using some sort of camera. Now the camera has some issues, and maybe the test images are shifted or they're broken or something or the other is happening over there, right? So, and you have to be robust to that. Our second challenge that arises is something called sample selection bias, which is also very common. So what happens here, and this is actually very common in healthcare style applications, where what happens is you gathered a bunch of training data, but maybe your test data is a little bit different. So one common example is maybe you gathered a bunch of training data about patients from a hospital, but in reality, let's say about a particular treatment, but maybe that treatment is only given to patients with certain conditions. So what happened was that your training data had some bias because you were missing out on patients which didn't satisfy that condition. And so the classifier that you would get would be somewhat biased. And, and at test time, when these other patients come, you may have a problem. This is extremely common in healthcare AI. First, when people start to do healthcare AI and try to deploy this is a very common situation. Another issue is privacy, which is also, a lot of the data that machine learning is done on now is very sensitive data related to people, and you have to preserve their privacy and so on. And what we have been doing over the last, since like last several years, is basically looking at the foundations of reliable machine learning. So about half of my group works on, so I'm kind of a learning theorist by training. About half of my group works on privacy and privacy preserving machine learning related stuff. And the other half works on kind of the foundations or the theory behind these other aspects of trustworthy machine learning. So that's where I'm coming from. And today what I will do is I'll talk a little bit about some of my group's work related to two of these aspects that I just talked about. So one is robustness, and the other is overfitting, and this also has some connections to privacy. Okay. So for robustness, what I mean is robustness to adversarial examples. So what are adversarial examples? I'm sure most of you by now have seen this particular picture, right? So what is going on over here is you have an image of a panda, and you can see on the, I guess on the left, there's the image of a panda, which looks, it looks wonderful. If you give it to a lot of these state-of-the-art classifiers that have been built on, some of these benchmark data sets like ImageNet, they're completely confident that this is a panda. Okay. Now what you do is you add 0.007 times the image in the middle, right? If you look at the image in the middle, it looks like, random Gaussian noise, and you're multiplying this by 0.007. So, what you're adding has very low magnitude. And then you get the image on the right. Now, to me, at least, this looks very much like a panda. It doesn't look that different, but a lot of the state-of-the-art neural network classifiers are completely convinced that this is a given. And, they're very confident of their, not only are they completely convinced, they're very confident of their prediction, so they're very confident that it's a given. And by the way, for those who don't know, which, I was one of them in the beginning, is that a given is a kind of monkey. Okay, so they're very convinced that this is a kind of monkey. Okay, so what are adversarial examples? Well, the image in the middle, right? So these are tiny perturbations to legitimate inputs that can cause misclassification, and this kind of drastic and serious misclassification. Okay, so they can also, classifying animals is, you can say this is a somewhat frivolous application, but, it can also get pretty serious. So for example, if instead of classifying pandas as monkeys, if you were classifying a stop sign as an yield sign, this could potentially lead to serious safety issues, right? So that's so that it could actually be quite serious. And so what is known about these adversarial examples? Well, there's a very large number of attacks. And it's very well, it's very well understood how to find them. We can find them very, relatively, we can find them quite efficiently. We can find high quality adversarial examples, which are a tiny bit different from legitimate inputs and so on. There are a few defenses. There are a handful of defenses. However, there isn't a lot of, understanding on why they happen, right? And what we are going to look at today from a more foundational or theoretical point of view is, why do we have these adversarial examples? Okay. So why do we have adversarial examples? Well, if you look at it through the lens of learning theory, there might be three possibilities. So one possibility is that they might be happening because your data distributions overlap, right? So you have pandas and you have gibbons, and maybe they just sort of overlap, right? Pandas, some pandas look very much like gibbons. Maybe it's plausible. So that may be one of the reasons. The other possible reason is that maybe the data distributions don't overlap. Maybe, pandas are here in space, gibbons are here in space, but you get too few of these samples. Maybe you got 3 pandas and 4 gibbons, and you couldn't really tell apart which one, as a result of this, you couldn't really tell them apart properly, right? So that's another possibility. And the third possibility is that we are probably not using the right algorithms, right? So maybe the algorithms that we are using are not the best. And so even though you can probably tell them apart, robustly using the data that you have, maybe your algorithm isn't just finding the good classifier. Okay, and I will give you the answer ahead of time, and then I'll try to convince you for the rest of the talk that is true. The answer is mostly number 3. The answer is mostly number 3, and I'll try to convince you that this is true for the rest of the part of the talk. Okay. Okay, so let's look at what we are talking about. What we are talking about over here is classification, where what is happening is that we are given pairs of the form xi, yi, where xi's are feature vectors and yi's are discrete labels. And what you want to do is to find a prediction rule in a class that will predict the y's from the x's. Okay, and this is the statistical learning framework that I just mentioned. This is kind of the classical machine learning textbook 101. Here what is happening is that your training and test data is being drawn from some underlying distribution, and what you want to do is you want to find a classifier f based on your training data. You want to find a classifier f that would maximize the accuracy, which is the fraction of times f of x predicts the right label. Essentially, that's your definition of accuracy. Okay. Okay, so how do we measure robustness here? So when we measure robustness, we will talk about robustness with respect to a metric, right? And typically in these adversarial examples experiments, the metrics that people use are either the L1 or the L infinity metric. So here what is happening is that we say that the classifier F is robust with radius S at a particular point X if for a distance metric D, the distance between X and X prime less than equal to S implies that f of x is equal to f of x prime, right? So what does this mean? So what this means is that the classifier, you have a point x which comes from your distribution. So you have a point x, maybe it's a legitimate panda image. Your classifier will predict panda in a small ball of radius s around that image. Right? So that is what being robust with radius S means. And what this means is that there are no adversarial examples around S, or at least, within distance S of X. Okay. So what are the metrics that we will look at? So we will look at two kinds of metrics here. So one is, of course, accuracy is, of course, important, because I could be perfectly robust by predicting panda all the time, but, that's not super useful. So accuracy is, of course, important, but we'll also care about adversarial accuracy, which is accuracy against adversarial examples at radius S. Okay. Okay. So let me first start with robustness in neural networks. Oh, I see there's a question. Let's see on chat. How is distance measured in the previous slide? Sorry. Oh, sorry. I went to the next slide. Yes, so the distance metric is given to you at at training time. So if you cared about, let's say, L infinity, or if you cared about L1 or L2, it will be given to you at training time. That's assumed. And of course, I realize that there are some very interesting questions about what should be the distance metric. But for now, let's assume that it's given to you. Okay, so let's start out by looking at robustness in neural networks. Okay, so how do we model neural networks? So here, what we are going to assume is that a neural network is going to compute a function f of x, right? So it's a very complicated, think about it, your x is an image, it computes a very complicated function, and then it will just output sine of f of x, right? So we are looking at binary classification. So we are assuming that there are just two classes, just to keep things simple. I mean, it all works for multiple classes, but it's just, there's a lot of mathematicalness. So let's just assume that we have two classes. And what we are going to do is we are going to assume that the robustness comes from local smoothness. So if you have an input x, right? If your f is locally Lipschitz around x, or locally smooth around x, and f of x is quite far away from 0, then f is going to be robust at x. Okay. So what is known about neural networks? Well, for neural networks, what is known is that there's a very large number of attacks. Again, that's known. There are a few good defenses. However, all the defenses show a robustness versus accuracy trade-off, right? So as soon as you make them robust, what happens is that their accuracy goes down for a lot of, somewhat more complicated data sets, okay? And the question that we are going to ask ourselves today is that, is this trade-off inevitable, right? So that's the kind of thing we're going to look at. And what I'm going to argue today is that that is not true in principle, at least for real data, okay? So what do I mean by this? So let's start out with a definition. Okay, so we say that a data distribution is R separated if for any 2 points, x, y, and x prime, y prime drawn from it, if y is not equal to y prime, then x and x prime are more than distance twice r apart, right? So what this means is that if you have points with 2 different labels, they're going to be at least twice r apart, okay? So why is this definition important? This definition is interesting because if your data distribution is R separated, then you can get both robustness and accuracy, right? And it's not too hard to show, but basically what we can show is that if your data distribution is R separated, then there exists a function f. Remember how neural networks compute a function and then we get a label by rounding that function. So there exists a function f so that f is locally smooth and sine of f has accuracy 1 and robustness radius r, right? So, and you can, this always exists, right? So this raises the question is what happens with real data, right? Like, is real data R separated? And to understand this, we did some measurements. So we picked 4 standard data sets. So these are, data sets on which people do a lot of adversarial examples, experiments. Okay, so MNIST, CIFAR-10, SVHN, and restricted ImageNet. And we measured the separation. So this is the separation between, the separation is the minimum distance between any 2 points in different classes, right? And here we are looking at, if I recall correctly, here we are looking at training, I mean, any 2 points between, any 2 training points, but, you get similar results if you look at also test training. So the adding test data into the mix doesn't make a big difference. So the separation, so if you look at, so coming back to this, so what you have, so the first column has the data sets, the second column has the separations, and the third column has the typical, perturbation radius, right? So the typical distance of the adversarial examples, right? The typical distance values that you use in adversarial example experiments. And what you can see if you look closely is that, so generally you would have a good solution if the separation was twice S or more. But what you see is that the separation is often a lot more than that, right? So for MNIST, for example, the typical S that people use is like 0.1. The separation is 0.74. And this is, by the way, an L infinity metric. Okay. In CIFAR-10, typical S is 0.03, but the separation is like 0.21, right? So which is quite a bit more. Okay, so you can see that there are asterisks next to SVHN and restricted ImageNet. So for these 2 data sets, what happens is that there's a handful of points where I think there are 2 images, there's one image which is exactly the same, but it has 2 different labels. So, there's maybe an image of a 0 which has been labeled as 0 and 9. Probably they arose due to labeling error. I'm guessing. I mean, I don't exactly know how the data sets were curated. But so what we did was we removed those points before we calculated the distance, because if those points were there, then this distance would be 0. And if you remove, and in each case we removed, I think SVHN we removed maybe 6 points, and maybe restricted ImageNet. Sorry, SVHN we removed, I think 4, and restricted ImageNet we removed 6 points. And, in any case, we removed less than 10 points. And with that removal, this was the result. Okay. So what you see is that real data, I mean, other than maybe 1 or 2 pairs which has labeling mistakes, real data does happen to be really R separated, okay, much more than R separated. So what this means is that in principle, there is no robustness accuracy trade-off, because there is a function that will, that will separate these data points without, compromising on robustness or accuracy. However, in practice, there is one, right? And so the question is, what accounts for this gap? So we tried to look into it by through an empirical study. Oh, I see some questions in the chat. Let's see. That is an excellent question. So one of the attendees is asking, how do we measure the distance, and do different distance functions have different 2R values? Absolutely. So this particular result that I showed you was for L infinity, but you can also look at L1 and L2. So we did that in our paper. And, of course, the exact numbers change, but the trends did not change. So also for L1 and L2, of course, the R and the S changes. But the fact remained that twice R was much more than S. So that definitely, that fact remained the same. We saw the same trend, but of course, the actual numbers changed. Okay, excellent question. Okay, so sorry. Yeah, 4 standard image data sets. We looked at 7 models, 7 different training methods. So this is work in 2020. So this was, kind of the methods that were kind of state of the art at the time. And in each case, what we did was we measured local smoothness, accuracy, as well as adversarial accuracy. Now, local smoothness for neural networks, you can't really measure exactly because that is an NP-hard problem. So we used an approximation. And it's an under approximation in the sense that we may be underestimating the local smoothness. Okay, so the question that we asked is that, is local smoothness really correlated with robustness? And again, this is kind of a typical, this is a typical setting that we saw. And again, I don't want to bore you with 7 sets of data, but this is essentially the typical kind of thing that we saw. Here in the red, what you see are these methods called natural training, gradient regularization, and locally linear regularization. These are methods where what happened is that the accuracy was high, relatively high. And then in gray, what you see are the 3 kind of robust methods where what happened was that, these are robust self-training, adversarial training, and trade. So these are kind of the 3 standard robust methods. So in this case, what happened was that the accuracy is relatively low, but the adversarial accuracy is high, right? Whereas for the red methods, what happened was that the accuracy was high and the adversarial accuracy was low. And if you look at them and what we also did was that we measured the Lipschitz constant. So Lipschitz constant measures, it's a measure of smoothness, and higher Lipschitz constant means less smooth, right? It means that the higher Lipschitz constant means that the function moves around very rapidly and it's very jagged, right? And what we see over here is the following. What we saw was that the red methods were less smooth and more accurate, whereas the gray methods were more smooth and less accurate, right? And this is already kind of, it's slightly counterintuitive for those of us who are used to, learning theory about, for example, things like support vector machines or linear classification, where the opposite is true, right? Like things that are smooth tend to generalize better, tend to be more accurate, whereas here what we see is a little bit different. Okay. And then the other thing we noticed is that the smoother methods tend to have a much higher generalization gap, whereas the less smooth methods tend to have a lower generalization gap. Okay. So what is going on over here? Lower generalization gap, right? So what is going on over here is that the generalization gap is pretty high for these gray methods. So one of the things we tried to do was to see whether we could reduce it. So for example, one of the standards method for reducing generalization gaps is something called dropout. So we tried with dropout, and here is kind of what we saw. So so we tried with dropout, and here is what we saw. So what we saw was that we combined dropout with all these RST, adversarial training, and trades, and what we saw was that it reduced the generalization gap a little bit, right? The numbers in parentheses was the generalization gap before, but it didn't reduce it by a lot. Okay. I see some questions on the chat. Yes. So Arpan is asking if the smoothness measures some sort of average over all training or testing points. That's an excellent question. It's the average over the test points. Theodora is asking, how is the generalization gap computed? So the generalization is the gap between, the particular loss on the training and on the test, right? So you can measure adversarial accuracy on the training points versus the one on the test points. So that's kind of that's the generalization gap. Okay. Or, the standard thing is you measure the accuracy on training, and usually with training, you stop training when you're completely accurate. So the training accuracy is very high, and then the test accuracy is a little bit lower, right? So the difference between that is the generalization gap. Okay. Okay, so what do we learn from this? So one of the things that we learned here is that the smoother methods like trades, RST, and adversarial training, they are definitely more smooth. They are leading to smoother networks, and they are more robust. However, these smoother methods have a large generalization gap, right? And, this is, as I said earlier, this is actually quite counterintuitive, because if you look at, for example, support vector machines, their smoothness will mean the norm of the support vector, right? And the smaller the norm, and the smoother it is, so the smaller the norm of that, of the classification vector, right? And the smaller the norm of that classification vector is, the better generalization you have. And there's like a lot of theory to support it. There is also a lot of, empirical experimental work that supports it. Whereas with neural networks, it turns out that things are the other way around, go the other way around. So which is, kind of counterintuitive. And I don't have an explanation for this. I don't have a theoretical explanation for this. And I don't think anybody does have a convincing explanation. And then the other thing we learned is that the dropout does reduce the generalization gap, but a very little bit. It doesn't really do that much. It reduces it by a little bit. And, but it doesn't really do that much. So in conclusion, what we see here is that real data is R separated. What that means is that robust and accurate networks do exist. However, the current algorithms that we are using, they don't find them, possibly very likely because they're not generalizing well enough, right? So the problem is not really the existence. The problem is really the generalization. And so what this means is that what we need is better methods for adversarial generalization. Okay. Okay. So coming back, now let us come back to this other, to this kind of place that we started from, where why do we have adversarial examples? Remember, we talked about these particular three possibilities. And what we showed is for neural networks, one is not what is happening. And, two, we don't really know, and possibly it's some mix of 2 and 3, right? So either our algorithms are so the robust algorithms that are so-called robust, they're not generalizing well enough, and the accurate algorithms are not robust, so we need better, and the algorithms that do generalize, which are the accurate algorithms, they're not robust, so we need something that gets us robustness, okay? So, coming back to these, this is where we are. Okay. Now, before I go on to the next topic, I'll look at one other case. So this was the neural networks. Now let's look at one other case, which is non-parametric methods, right? And these non-parametric methods are, these kinds of simple, pattern recognition style methods, which have been used for a very long time. And they're, I guess, still used in applications like financial data and so on, and discrete data kind of stuff. And these are things like nearest neighbors, decision trees, so on and so forth. Okay, nearest neighbor, decision trees, and things like that. And there are also other more complicated ones like random forests, kernel classifiers, and so on and so forth. Okay. So what is known about non-parametric methods? So what is known there is, so before I get to that, it turns out that there's a lot of theory about them. And before I get to that, let me define one thing, which is the Bayes optimal classifier. Okay, the Bayes optimal classifier is the one which has the highest accuracy on the data distribution. Okay, and notice that I said data distribution. And the data distribution. So what this means is that this is only reachable in the infinite sample limit. right? So if your n goes to infinity, you will reach it, but you don't know what it is unless you know what the distribution is, right? So you can only reach it in the n tends to infinity limit. Okay. So what is known about non-parametric methods? Well, this was a theorem which was proved by Stone in 1977. And believe it or not, this was before even I was born, let alone my students. So what they showed was, it's really timeless work, right? So what they showed was that as the size of the training data grows, the accuracy of many of these non-parametric methods, so things like, k nearest neighbors, if you're setting k properly, and decision trees and so on, converges to the accuracy of the Bayes optimal classifier. So if you get enough data, and usually enough is a lot of data, right? If you get a lot of data, then what would happen is that you will slowly converge to the Bayes optimal, the accuracy of the Bayes optimal classifier. Okay. Well, what about robustness? This result, however, doesn't apply to robustness. Okay. So before I get to this question, let us first ask ourselves, what is the limit of robust classification? Okay. So if you remember the Bayes optimal classifier, well, the Bayes optimal gives you the maximum accuracy on a distribution, but it's undefined outside the support of the distribution, right? And in fact, you can have multiple Bayes optimal classifiers, which and some of which may not be robust, right? So if you look at these blue curves that I have drawn, these are all Bayes optimal because they are classifying the distribution correctly, but they're not really robust because they're passing very close to these gray points and the red blobs, right? So what we can do, however, is we can define this object. It turns out we can define this object. And, of course, the way it looks like, so the R optimal classifier is the one that maximizes this kind of robust accuracy, right? And the way it will look like is, so here is an example. I mean, of course, this will depend on the distribution, and it may also differ from the Bayes optimal. It might take a different path from the Bayes optimal. So here is an example of what it looks like for an R separated distribution, right? Where the pluses and minuses are separate by at least 2R. So here is an example. So for example, you could predict plus, where if your distance between, on an example X, if the distance between X and the support of the positive class was less than R, you could predict minus otherwise, right? So this would be an example, this would be an what it would look like. But again, it's also, again, not unique, right? So you can have multiple, if your distributions are really well separated, you can have many R optima, right? So, but anyway, so this is the R optimal classifier that we can define, right? So this is the limit of robust classification. So if we had an infinite amount of data, this is what we want to get to, okay? And so what we can do again is, we can look at, so now the question is, when do we converge to this R optimal? And what we can do is we can also establish such conditions, right? And, so they are a bit like Stone's theorem, right? So they are the conditions that, they're a bit like the conditions involved in Stone's theorem, but they're a little bit stronger. And I won't go into the technical details because I know it's a broad audience, and we can characterize these conditions. However, the interesting thing is that what converges to R optimal. So it turns out that things like nearest neighbor classifiers and kernel classifiers, they will converge to R optimal as n goes to infinity. And if you set k properly, right, in the well-separated case at least, so they will converge to R optimal. But interestingly, there are a group of classifiers that converge to the Bayes optimal, but not the R optimal. And these are classifiers like, histograms and decision trees, right? So they will converge to the Bayes optimal as n goes to infinity, but they won't necessarily converge to the R optimal. Okay. And so what happens over there? So just to give you some intuition about what happens over here, let me show you a very toy example of a decision tree, right? So here you have this red class and you have the gray class. And if you try to build a decision tree, what would happen is you would just choose this blue line, right? That separates so that you have, kind of one root node, which corresponds to the blue line that separates the grays and the reds, and you're done. And that is good, but you're not going to be robust, right? And, even if you had an infinite amount of data, you would still choose this blue line and you will be done. Whereas the robust decision tree, there is a robust decision tree, and that is kind of the zigzag line, right? So the robust decision tree, however, is this kind of zigzag line, and you wouldn't get to it with the current decision tree building algorithms, even if you had an infinite number of data points. Okay, so what does this mean? Well, what this means is that the robustness depends on the training algorithm, right? So in conclusion, what we did over here is we looked at the R optimal, which is a new large sample limit for robust classification. We showed that classifiers like the nearest neighbors and kernels converge to this R optimal for well-separated data, but not things like decision trees. And what this tells us is that for non-parametric methods, the robustness, again, also depends on the training algorithm, right? So if you come back to these three cases that we had talked about, we have separated data. So one is not the problem. The overlapping distribution is not the problem. We have an infinite number of samples. So samples is not the problem. The problem is the training algorithm. Okay. Okay, I see a bunch of questions on the chat on robustness. So maybe let me answer that. So Arpan is asking, Theodora is asking, you mentioned you tried a number of training algorithms. Insights are true for training algorithms with guarantees such as interval bound propagation. So we didn't try those guaranteed robustness algorithms. That's a very good question. We did not try them. They do also have a gap between robustness and accuracy. They also definitely have gaps between those. So my suspicion would be that, probably something similar is going on, but they also have these kinds of gaps. Okay. Arpan is asking, among reasons for existence of adversarial examples, what are your thoughts regarding the dimensionality of input data? So my take on this problem is that even if the dimensionality grows, if the data stays well separated, then in theory, you should at least be able to find adversarial, you should at least be able to find robust classifiers, right? So for example, if you think about linear, in the linear case, you can show that the most robust classifier is the support vector machine, right? So you can find it. So even if your data dimension grows, in theory, you should be able to find it. I think with neural networks, what is probably happening is that their generalization probably works in a very different way, right? There, the neural networks are probably generalizing for very different reasons than linear classification. And that's why we see this kind of strange things that we see. Okay. Amir is asking, could deep neural networks be robust and accurate using a modified training goal or cost function? I guess my answer is that, I don't know. That is quite possible. That is quite possible. I don't know. That is quite possible. But one thing to also keep in mind is that with deep learning generalization, there are other aspects than, just the cost function. So for example, there are things like architecture. So it's also quite possible that the robust architectures that are robust need to be very different from architectures that are simply accurate. Or the optimization methods also, there's a lot of work by like Nati Sibro and Ben Reich, which have shown that the different optimization methods also generalize differently because they get to different local minima, right? So maybe there are different optimization methods, right, other than Adam or SGD, that will lead to better generalization. So I think it is a fascinating question. I think what has happened so far is that people have tried a lot of different loss functions, right? People have tried a bunch of different loss functions. People haven't really tried as many architectures or optimization methods just because it's just harder, right? So yeah, but it's quite possible. Chu Shanjon is asking, in your decision tree example, are you suggesting that training methods that favor simpler representations could converge to classifiers that have bad robustness. That is exactly true. In that particular example, yeah, that would happen. Suwei is saying, you mentioned that experiments are performed to see if machine learning algorithms converge to R optimal. No, our results for convergence to R optimal, these are theoretical results. These are not experimental results. So these are theoretical results which said that as n tends to infinity, you converge to the R optimal. Okay. Okay. So maybe let's move on to the next part, and I'll try to be quick with this, where what we will look at the next topic that I wanted to talk about, which is overfitting. Okay. So, so here what we'll be talking about is deep generative models. So, I mean, by now everybody's heard about GANs and seen all these deepfakes and so on and so forth. So they have been highly, highly successful, right? But a question that remains is that, do they overfit, right? And, the question is, what does overfitting even mean in this context? Okay. So what kind of overfitting are we looking to, detect? Well, here's an example of a kind of overfitting, which might be actually quite dangerous, right? So suppose you have a bunch of, you trained your generative model on a bunch of faces, and now you expect it to generate new faces. But maybe what it's doing is that it's taking your training data and then spitting it out. Or maybe it's taking your training data, making very minor changes, and then spitting it out. Right? So this is the kind of overfitting that we are hoping to detect. Okay, so it reproduces training data or maybe slight changes to the training data, right? So why is this kind of interesting? So it can be quite a bit of, it can be quite a concern in, for example, healthcare applications. So for example, now that there are these generative models, what some people are doing is that they are training GANs on real patient data, and then they are releasing synthetic data from these GANs, and then, the hope is that these will be private because this is synthetic data. This is not real people's data. But if your GAN was spitting out real patients, then this could be a serious privacy concern, right? So this is kind of the reason why we care about this kind of, this kind of overfitting, okay? So now let us look at how we define overfitting, okay? So this is kind of the setting that we are talking about. So we have a bunch of training data, which we get from some underlying distribution. We use it to build a generative model, and then the generative model may spit out a bunch of generated data. Okay. What we also have at our disposal is an independent test sample from this underlying distribution. And using this test sample, the generated data and the training data, we give it an evaluation score. Okay, so here the training and the test data are drawn IID, and the training and the test data, of course, don't overlap, and they come from the same distribution. And what we want to do is, using this training, independent test, and the generated data, we want to give it an evaluation score. Okay. So what is the classical view of overfitting? So in the classical case, what we would do is we would calculate what is called the likelihood. So here what we have, and we would get a figure like the one you see in this on this slide. So what would happen is we would make our models, keep making them more and more complex. And then what we would do is we would plot the training likelihood, which is the red line, and the test likelihood, right? The likelihood of the training data, which is the red line, and the test likelihood, which is the blue line. And what will happen is, as we make our models more and more complex, the training likelihood will keep going up. The test likelihood will go up for a while, which means that you are fitting the data well. And then after a while, you'll start overfitting. So then the test likelihood will go down. And if there is a big gap between the training likelihood and the test likelihood, then what that means is that you're overfitting, right? So this is kind of the classical view. Again, this is what you see in Machine Learning 101, okay? So why can't we use this kind of thing? Well, with this kind of big, deep generative models, there are, this kind of thing doesn't always directly work, right? First of all, your deep generative models, they may have intractable likelihoods. So things like VAEs, you can't really compute the likelihood directly. You can only approximated, right? You can compute a lower bound approximation. The other issue is that, for models like GANs, there is no likelihood, right? You can't really get a likelihood. I mean, you can kind of approximate it, but who knows what that means. What you can do is you can get only samples from this distribution, right? So you can only get the generated samples. You can't really get the likelihood, okay? And in these kinds of cases, overfitting is a serious concern, right? Because, your training data is huge. Nobody has time to look through and remember all the training data, right? So you won't manually catch it that easily. And the models themselves have tens of millions of parameters, right? So, it may well happen, right? Okay, so what we will do today now is we'll talk about, when we started looking at this problem, we realized that there were two orthogonal kinds of overfitting going on here. So what I'll do today is I'll talk about these first. I'll talk about these two formal notions, and then I'll talk about how to detect them. Okay. So it turns out that there are two formal notions of overfitting, that is overrepresentation and data copying. Okay. So what is overrepresentation? So we say that a particular generative model is overrepresenting a particular region if under the generated distribution, you are much more likely to generate samples from this region than under the original data distribution, right? So for example, maybe, to put it, very, very concretely, if your data distribution has half dogs and half cats, and now maybe 80% of the time your generative model generates a cat, then you are overrepresenting cats. Okay, so this is the idea. Okay. Orthogonal to this is a notion of something called data copying. Okay, so what is data copying? Here, what you have is a training data. You have the generated data and test data as usual. But what you also have is an underlying distance metric D. Okay? So you are data copying in a region C if, on an average, if you look at generated data, right, and their closest training point versus test data and their closest training point, the generated data is much closer to their closest training point than the test data, right? And remember, the test data is an independent sample drawn from the same distribution, right? So imagine if you were actually spitting out training samples, then the distance between the generated data and its closest training point would be 0. Whereas the test data, the test data would be another independent phase. So, there would be some distance, it would be some distance apart. And so the data copying, this particular condition will be true. Okay. So notice that overrepresentation is very similar, but it's somewhat similar, but it's not data copying. Okay. So to give you a concrete example, suppose your underlying data distribution is a mixture of 3 of these gray Gaussians, right? In the first case, what is happening is that you are picking off 2 of them very accurately, and you are drawing samples. So that's the red. And there you are overrepresenting, but you're not really data copying because you have learned these 2 Gaussians very, very, you have learned them properly, you have generalized quite well. So, you're just speaking from these 2 Gaussians, right? So you're really overrepresenting, you're not really data copying, okay? Whereas if you look at the example on the right, what is happening over here is you are data copying, because what is happening is you are, you have again these 3 Gaussians. You are basically spitting out a slight difference from the training data, right? Like you are taking the training data, perturbing it tiny bit, and then spitting it out. So you are data copying, but you are not really overrepresenting any of these individual Gaussians, right? Because if you look at the individual Gaussian level, you will see that you have the same number of training and mostly the same ratio of training and generated points, right? So you have data copying, but no overrepresentation. So prior to our work, and also, prior to our work, there was a lot of existing hypothesis tests on detecting data copying, and, these are just some examples. There are many, many more. I mean, but what we realized as we started going through the literature is that almost all of them test for overrepresentation. And what is even more interesting, that except for one test, which I will compare with, which I will baseline with later on, except for this one test, they all fail to detect even exact data copying. So all these generative model overfitting tests that you have, and there's a very large number of them, kernel, MMD, this, that, and the other, All of them will fail if your data, if your generative model is just spitting out the training samples. They'll say, oh, this is great. It does not overfit. Okay. So, okay. So now let us try to look at a simple test of data copying, how to detect data copying. Okay. So here is a simple idea. So we can just go from the definition, right? So you have training data, generated data, test data, and a metric. You check if the average distance between the test data and the closest training point versus the average distance between the generated data and the closest training point, if they are very different, right? Okay. And so you can do this. You can, if you are given a generative model, if you have all the stuff, you can do this. But the problem with this test would be that if you have some outliers, you are going to get very high variance. Okay. And you can do the usual statistical testing things, right? So you can look at the variance. You can see if this difference is more than, 3 sigma, and then, do the usual statistical test kind of things, right? But the problem with this particular test is that you'll get very high variance from the outliers. Okay. So how can we solve this? So the solution to this is, instead of looking at absolute distances, what you could do is you could look at comparisons instead, right? So what you could do instead is you could compare the following. You have the training data, test data, and the metric. You look at if on an, if you can go over all pairs of, test and generated, and look at if the distance to the closest one for the test one is greater than the distance to the closest one for the generated one, and so on. Okay. So this looks kind of complicated, but what this is actually, if we go back to our Stat 101, what this is actually is something called the Man Witney test, right? So which is a very standard statistical test on the distances between the test points and their closest training points versus the versus the generated points and their closest training points, right? So this is the Man Witney test, and this Man Witney test is, it's a non-parametric ranking test, and it's known to work really well. So that is what you could do, right? So this is what you could use. Okay. So this is well and good. So we did this kind of, we did this kind of thing, and, we just use the comparisons. This is well and good. But the real problem with these generative models is that there's a lot of heterogeneity, right? So when you are modeling cats, the model will behave one way. Then you're modeling dogs, it will behave in a slightly different way. Some places things will be distorted. So what would happen is that for these kinds of heterogeneous models, global tests may fail, will in fact fail, right? Because you can have data copying in one region of space, you can have underfitting in another region, maybe you don't model a third region properly, and then you have overrepresentation somewhere else, and everything will just be a huge mess, right? Everything will just cancel out. So the question is how to account for this. So what we did was we used an algorithmic tool, which is used in, a lot of standard, classical non-parametric statistics, where what we do is we divide the space into cells, right? So we divide this entire space into cells through some clustering. Then we do the test in each cell. We carry out the test. And then finally, we report the weighted average of the one-sided test results. Okay. So, what happens is we look at this test results, we look at this weighted average test score. And if that looks high, then we can go inside each cell and do the test inside each cell to see where things went wrong. Okay. So now we'll come to, so now we have the test. Now the question is, how does it work and what does it detect? I see some questions. So Arpan is asking, is the overrepresentation similar to the mode collapse of GANs? So the overrepresentation is the opposite of mode collapse, right? So, if you think about underrepresentation, that would be mode collapse. So overrepresentation is like the opposite of mode collapse, right? Like the complete opposite of mode collapse. Okay, that's a very good question. And in fact, there are lots of tests for mode collapse, right? All these overrepresentation tests and so on, they will basically detect mode collapse, but they won't detect this kind of data copying. Okay, so now let's look at evaluation. How do these things work and how well does it detect data copying? Okay, so I'm going to show you, I mean, we have more in our paper, but I'm just going to show you two sets of experiments. So the first is a case study involving variational autoencoders in MNIST. And where what we did was we varied the latent dimension. So we have an this variational autoencoder. Higher the latent dimension, the more complicated the model. Okay, and if the latent dimension is 1, then it kind of underfits. There's not that much it can do. And it's known that if the latent dimension is 100, then it's really overfitting in other ways. So there are other papers which have shown that it is overfitting in different, other different ways when the latent dimension goes all the way up to 100. And then the metric that we used was the 64-dimensional latent space of an autoencoder, which was trained with the VGGNet perceptual loss. So this is kind of a standard autoencoder, which it's not related to this particular variational autoencoder that we are testing, but it's a different autoencoder, and it's kind of a standard perceptual loss that you can use for, a perceptual metric that you can use for MNIST. Okay. And here is what we saw. So what we see is, so maybe let me explain what we are seeing. So here what we have is our test score. So we have 3 baselines. Our test score, CT, the generalization gap, the thing that I mentioned earlier, right? The difference between the test likelihood and the training likelihood. Remember that for VAEs, we can't get the likelihood, but what we can get is something called the elbow loss, which is the which is kind of a lower bound on the likelihood, right? So this is a lower bound on the likelihood. So we can get the elbow. So, and then the third one is something called the nearest neighbor test, which is, the one test that works and which can detect exact data copying. So this is a paper by Lopez Paz and Okwab in, I think it was 2016, right? So this is a 2016 paper by Lopez Paz and Okwab. So what do we see over here? So what we see is that what we are doing is that the latent dimension is decreasing, right? What this means is that we are going from overfitting on the left to underfitting on the right. And what you see is as you go from overfitting to underfitting, our test score goes up, right? It, with some variations, it mostly goes steadily up, and it crosses, and it crosses this 0. 0 is where it should be properly fit, right? It crosses 0 at some point. Okay, so it's kind of doing what we expect it to do. For generalization gap, what is happening is that the elbow is not very informative, and it's possible because there is a large, this may be because of several reasons. So the elbow, as you see, the generalization gap here is not very informative, right? The generalization gap is that blue line in the generalization gap figure. And this may be because of several reasons. So one thing may be that there is too much gap, right? The lower bound versus the likelihood, there's just too much gap. The other reason, maybe there might be some optimization style reasons. I don't know exactly what it is, but what we found is that it was not super informative. And finally, if you look at the nearest neighbor test, so for the nearest neighbor test, you do see things going up. But this 0.5 is what should be, a good fit should be 0.5, but the numbers don't mean very much. So as you go from overfitting to underfitting, the score goes up. But it's hard to interpret because everything is above 0.5, which should be perfect fit. Okay. Okay. The second case study that we did was we looked at Big GAN, which is a very big generative model. So well, I don't really have the resources to train Big GAN, or anybody in my group does not have the resources to train Big GAN. So what we did is we took a pre-trained model, and we looked at 3 classes. So these are kind of, 2 of these are the default classes. If you download Big GAN in PyTorch, so Coffee and Bubble. And then the third is, we just took a random class which has an object in the foreground. So this is Schooner. And then what happens is that So as a metric, we took the 64-dimensional PCA of inception space. So the inception metric is, one of these common metrics that people use. So this is basically the feature space of a neural network that is trained on ImageNet, or a particular architecture, or neural network of a particular architecture that has been trained on ImageNet. So we took the 64-dimensional PCA of this space. And then what happens is that BigGAN has something called the truncation threshold, which measures how diverse the samples are. So we control the truncation threshold. So instead of underfitting versus overfitting, we just control the truncation threshold, because we are not able to retrain it many times. Okay. And this is kind of what we saw. So remember, for BigGAN, there is no generalization gap, since there's no likelihood or approximation. So we have the nearest neighbor, and then we have our algorithm. So the nearest neighbor algorithm, it's all flat. So there are 3 different versions of the test. It's all flat, right? As you change the truncation threshold, nothing changes. Here, what happens is you change the truncation threshold. And again, we are going from, so we are again going from, I think, overfitting to underfitting, right? So it's the same way as going from left to right. As we are going from overfitting to underfitting, what we see is, sorry, I hope I didn't get the sign wrong. Yes, I got the sign right. Okay. So here we are going from overfitting to underfitting. So the truncation threshold, what it does is it truncates the noise to a threshold, right? So if the noise is truncated to a really small threshold, then what will happen is that it will generate things very close to the training sample. And so it's a form of overfitting, you can say, right? It's a form of data copying. So the truncation threshold, we are going from overfitting to underfitting. And you can see as we go from there, our test scores increases, okay? Whereas the other one stays flat. And before I end, just to give you some idea of what we are finding. So here are some samples from a data copied cell, right? So the real samples, the test samples are on the top row, and the generated samples are on the bottom row. And then we have some samples from a non-data copied cell. And you can see that in the data copied cell, what is happening is that, this is one coffee cup, which is getting generated over and over again from different kinds of viewpoints, right? Whereas in the non-data copied cell, what is happening is that the samples are more diverse, okay? So in conclusion, what we did was we formalized 2 notions of overfitting and presented a new sample, 3-sample test. So these are the papers that were, that this talk was based on. And finally, I'll just end with pictures of my co-authors. And thank you for listening.
Thank you very much, Kamalika, for this very interesting talk, telling us more about things that are still open and challenging on robustness. So let's see if there are more questions. Please feel free to post them on chat, or I can, if you want, figure out how to open up the mic for you.
Fatima has a question. My question is, based on your observations, would you say GANs and VIEs are differently prone to overfitting? That's a very good question. I don't know the answer. I think it depends very much on the data set and the parameters. My impression is, I don't think one is more prone than the other in general. I think the answer is very much dependent on, how you do the training, how you set the various hyperparameters and so on. That's just kind of my understanding. And, by the way, for generative models, setting these parameters is actually quite challenging and, takes a lot of parameter tuning, much more so than, for example, discriminative models. Thank you. There's a question from Kim. What are your thoughts on how the problems you raise apply to domain adaptation? How do we address those challenges? Yeah. So the problems that I talked about, they are actually quite close to domain adaptation, right? So robustness, you can think about robustness as a form of domain adaptation, where what you want to do is you want to be, in some sense, you want to perform well with respect to all domains where your where your test points could shift a little bit, right? So they are connected to domain adaptation, but they're less general. So I guess the question is, so they're connected, but they're less general. So I guess standard domain adaptation solutions might work, but the hope is to find better ones, right? That do even better than what we can get through domain adaptation. Chu Shanjun is asking, one takeaway, we need to rethink about blindly relying. Yes, that is very much the case. So Chu Shanjun is asking, and this is a very good point, we need to rethink about blindly relying on Occam's razor or, traditional learning theory if we want to train robust classifiers. That is absolutely the takeaway. And, on the theory side, what this means is that we need to also develop new theory, right? Like other things are going on with these deep neural networks, and we need to think about them and try to understand them better. Sue is asking, can you comment on whether the choice of distance metric matters? Absolutely. The choice of distance metric would matter in these tests. My suspicion, though, is that if you have a reasonable distance metric, you would probably get similar results. So the case where you wouldn't get similar results is, if you have like a borderline case. But if you are doing severe data copying, you would probably get similar results if you have a reasonable metric. So Kanab is asking, has the robustness of neural networks been tested if we add noise within our distance from a class X, right? Label the noise as X and train the network. Should the network by default be robust in this setup? So actually, adversarial training, right, is, one of these methods that I talked about. It does something similar. So what it does is, again, I'm abstracting out a bunch of things, but essentially what it does is it takes a point X, it finds the adversarial example to X, and then, labels that as Y, and then takes a gradient step, or, takes the optimization step against that. So it does work in training. But in the test case, what happens is that you do lose accuracy in the process. So generalization, I guess, is kind of a pretty big problem. Arash is asking, is there any kind of data set where you can't be robust at all? So you can always be completely robust if you're willing to sacrifice accuracy, right? So, for example, you can always predict the same label, cat, and then you are perfectly robust. But so if your data set is not R separated, right? So if your classes are distance less than R, then if you want to get robustness, you have to sacrifice accuracy. So the real question here is, what are the kinds of data sets? I think the question that you're hoping to ask is, what are the kinds of data sets where you have to sacrifice accuracy for robustness? And so those are the kinds of data sets. The data sets that are not R separated, you would have to sacrifice accuracy for robustness.
So one question that I have is that, would also the complexity of the model play a role there? Accuracy, robustness, there must be some like model capacity or model complexity that plays a role in the trade-off between accuracy and robustness.
That is, a very good question. I actually didn't go into this because it was a little bit of a distraction. So one of the other experiments we did in that paper is that we took these standard models, and, again, this is not like a real, it's not like a real experiment. I mean, this is more like a proof of concept, right? So what we did was we took some of these standard models and then tried to fit the union of the training and the test data robustly to that model. So we took the union of the training data plus the test data, and we said, okay, we are going to fit this robustly to this model. And we succeeded. right? So the standard models can fit the training union test data robustly. It's not that they lack capacity, but they can't generalize.
And then that's very interesting. So one other question that I had was, what is your take on these algorithms that combine nearest neighbor algorithms and neural networks? So I think they are called like deep K nearest neighbor, where representation is learned using neural networks, but then there's a K nearest neighbor that does the classification and separation.
So the K nearest neighbor step is actually robust. It's provably robust, right? But it will be robust with respect to the metric in which, so I think if they manage to get a good metric, which is, and then again, that metric has to be, to get robustness in the input space, that metric has to be smooth with respect to the input space. So I think if they manage to get a good metric, then it will be provably robust. But then the challenge would be how to find that metric. And it's actually quite an interesting problem. Yeah, I think. There's some more questions in the chat. Oh, could you please scroll? Sorry, list of papers. These are the list of papers. There's one last question. Theodora is asking, I'm thinking of the bias variance decomposition. Is there any parallel to bias variance in neural networks and overfitting in generative models? That's a very interesting question. I don't know. I mean, my takeaway from this generative models overfitting work is that, normally we always think about overfitting as this bias variance. But for these kinds of very complicated models, there might be more going on, right? Than this kind of, really classical view where all you care about is just the bias and the variance. There might be going on because these models are just so complex. And there might be, and I think, honestly, I think the real open question here is what are the other overfitting modes, or other modes of overfitting or other modes of failure of these deep generative models, right? Like where do they fail? What can they do? What can they not do? I think those are kind of the interesting questions here. Amir is asking, would you mind listing a few non-parametric methods? So examples would be, K nearest neighbors, decision trees, random forests, kernel methods. These would be all, the kernel classifiers. These would be all non-parametric methods. So here, what happens is that in non-parametric methods, what happens is that you're not, so the size of your classifier, the classifier that you will get will grow, the complexity of the classifier kind of grows with the data, right? Like if you're building a tree, unless your data is really quite well behaved, the size of the tree will grow with the data a lot of the times. So that's, yeah. Harold is asking a very good question. He's asking that, is there a similar trade-off between accuracy of a classifier and privacy rather than adversarial robustness? Or is it the case that the trade-off shouldn't exist in principle for real data? If you're talking about differential privacy, then there are all manner of lower bounds which show that, fitting a differentially private classifier you need a lot more samples to fit a differentially private classifier than to fit a non-private classifier. So for differential privacy, the trade-off, my kind of view on this thing is that the trade-off is not so much between privacy and accuracy, but it's between privacy, accuracy, and training set size, right? So if you think about it as 3 points on a triangle, and you can get 2 of this triangle, 2 points, but not all 3, right? So you can get privacy and accuracy, but you're going to need a lot more data. And you can get, so that's kind of the answer.
Maybe I ask also another question. Maybe my last question is, so you talked about this very interesting test for data copying. Could there exist efficient algorithms to run those kind of tests? Because the test you mentioned requires going through all the test and train and generative data?
That's a good question. So we used some sort of efficient data structure. So you don't have to go through. So usually what happens is that the test data is a bit smaller than the training data. So you can go through the test data, and the generative data, you can also make it more or less the same size as the test data. But the hard bit is usually going through the training data, right? And for that, we used kind of more sophisticated nearest neighbor style data structures. That's a good question. Yeah, and that we used this kind of sophisticated data structures. So that, yeah.
Okay, so that helps reducing
That,
the complexity.
Yeah, that helps. Yeah.
So Theo is also asking, is the data copying test a good metric for privacy leakage?
I don't think it's sufficient, right? Like just because you're not data copying doesn't mean you are private. Because what you could do is you could just add a very large number to every pixel, right? And you have your training data and you add a large number to every pixel, right? And then, that is very hard to undo, but you're not data copying, right? But it is it's some kind of a first test to detect if something is off.
Is there maybe last couple of questions from the audience?
I think there's one last.
Otherwise, we can wrap up. Thanks a lot.